Hello, everyone. Welcome to our sixth lecture of this quarter. So today I will start discussing quite a new topic of electricity and magnetism. This is kind of where 7C really takes a turn as far as topics go, although at the end of the quarter we'll connect things back to waves. Because this topic tends to be kind of a bit challenging and abstract, something very different, although a lot of the concepts that we'll talk about you'll probably have encountered in your previous science classes such as chemistry, but still it's quite a shift. I decided to take it a bit slow in lectures and in DLs as well. These topics are introduced at I think a pretty good pace. So also because this is midterm week, I will not overwhelm you too much with a lot of new material. The quiz next week, I'll still focus on older things. So, because I think this topic, this new topic, or at least the beginning of it, definitely needs a little bit of time to really sink in. So today will be a shorter lecture just to give you a bit of an introduction. And then next week, I'll record a new lecture, which is going to be a little bit more comprehensive, tying a lot of ideas together. All right, so the first thing that we start talking about, and this was the very last activity in your DL when you finished first with optics, and then you really, it was definitely a shift in topics when you started talking about charge. So hopefully you got a chance to see some of these videos that demonstrated how different charges interact with each other. So this is something that I'm sure you're all familiar with. There are two types of charges, positive and negative. And we know that when the two charges are the same, either two positives or two negatives, they repel. When they're different, they tend to attract. So how did people realize this, come to realize this? So that's exactly these little experiments that you saw in the video. And this is exactly the types of experiments Benjamin Franklin, as pictured here, was doing when he was first exploring electricity. So for example, there was one where there was this pipe, like a plastic pipe that you could rub with a type of cloth, like a silk cloth. And turns out that when you do that, charge gets transferred. So it gets transferred from the, so for example, electrons get transferred from the pipe to the cloth, or vice versa. We don't quite know which one gets positively charged, which one gets negatively charged, but because overall charge is conserved, it leaves one system and it enters the other. So that there you created two systems of opposite charge. So then the cloth and the pipe ended up attracting each other. This is something that I'm sure since your childhood have experienced every time you go down a plastic slide, and especially if you're wearing particular clothes that make it easy for that charge to get transferred, then that slide gets charged and you feel that static electricity. So how do we create two systems of the same charge? Well, you can take two pipes, and because they're made out of the same material, they'll get charged the same way. And then when those two pipes were brought together in the video, and you would have done this in DL if you were in DL, you would observe repulsion. And another thing that you observe is that not only do they repel or attract, but it also matters how close the two objects are to each other. So the closer you bring them together, the stronger is the force. The farther they're apart, the weaker the force becomes. So I included this quote from Benjamin Franklin that I really like because I think it really follows kind of the philosophy of Physics 7 and how we approach learning physics. So he said, "Tell me and I forget, teach me and I remember, involve me and I learn." So that's kind of the point here is, you can watch a lecture or watch someone else solve problems and you will learn some, it will give you a starting point. You might kind of remember some things, but to really convince yourself that you've learned something, you have to get your hands dirty in a sense, in that with that you have to explore, you have to try, you have to get stuck, you have to make mistakes, and then you have to get out of that, you have to fix your mistakes, and that's really how we learn. That's why we kind of really encourage students to think through these things really carefully, rather than just watch lectures, read books, and watch someone else solve problems. All right, so let's move on. So we like to start or make connections with things that we've already learned, or start with something that we are familiar with. We haven't really talked so much yet, or we're just starting to talk about this idea of forces between charges. But one thing that we can connect this to is the idea of potential energy. So 7A was a lot about energies and potential energies, and specifically, how does potential energy, how is that related to force? So we start with potential energy, and then we went to defining a force. So we'll do the same kind of analysis here with electric charges. We will first start talking about the potential energy that is involved with electric charges, and then we'll make the step to describing the force. So I know Savannah was a while ago for many of you, so let's kind of review some things. So here are familiar systems that we looked at quite a bit in 7A. So one was a spring mass system. So it was something, mass connected to a spring that oscillated about equilibrium. And we defined its potential energy. What did we say? We said that at equilibrium, the potential energy was 0, and it was non-zero, and you were away from equilibrium and it increased with the distance from equilibrium. Now, when you stretch a spring away from equilibrium, which way is the force? The force is always back towards equilibrium. The mass wants to return to equilibrium. If you compress it, the same idea. The force would point then down towards equilibrium. And that's consistent with our definition of potential energy, in a sense of potential energy decreases towards equilibrium. It's 0 at equilibrium. It's higher than 0, bigger than 0 away from equilibrium. So what we see here, if we look at this initial and final state, our potential energy decreased in the direction of the force. Now, another system that we looked at a lot is objects that are interacting with the Earth due to the force of gravity. So there we also defined the gravitational potential energy. So here we called it the spring mass potential energy. Here we called it the gravitational potential energy. And what did we say? That gravitational potential energy decreased with height, or decreased with lower height, or increased with higher height. So the higher you bring the object, the higher is the potential energy, the lower is the lower. So in this case of a ball falling down, let's say there's just a state of free fall, there's only the force of gravity acting on it. Between the initial and final state, the height decreased, so the potential energy decreased, and that exactly is the direction of the force. The force was down, so just kind of reviewing that idea that force points in the direction of decreasing potential energy, like we see that in this example. So nothing is different when we start talking about electric charges. So here let's look at this example of some big object that's held in place and it's overall positively charged. And now let's take a negatively charged, a negative charge, and bring it close to this object. So what do we know? We know that the electric force will point in this direction towards the positive charge. How do we know that? Because we know that opposite charges attract. So if it points towards there, what can we conclude if we assume that the connection between force and potential energy is universal, which it is? We can conclude that potential energy must have decreased from the initial to final state. So the change in potential energy is negative when you move a negative charge closer to a positive charge. And in terms of also conservation of energy, what does that tell us? Well, it tells us that if potential energy decreased, some other energy increased. What is that other energy? It must be kinetic energy. So imagine if you were holding this charge in place and then you let go of it, what would happen? It would speed up towards the positive charge, decreasing its potential energy, increasing its kinetic energy. And of course, this whole analysis would be true if the charge held in place, our kind of source charge here, was negative, and our test charge, the charge that we're thinking about the forces acting on it, would be positive. So just the situation where two opposite charges are interacting. Now, what if we have take two like charges? So here we still have that positive source charge, but then we have positive test charge. Now we know that because they're the same charge, they will repel. So now the electric force will point in the opposite direction. So if we try to bring this positive charge closer to the positive charge, we are changing its position in the opposite direction of the force. So then the potential energy must increase in this case. So it increases when we bring the positive charge closer to the positive charge, but it will decrease if we go the other way, if we take this positive charge and move it away. So here, the statement is a potential energy increases in the direction opposite of the force. And then, of course, kinetic energy would decrease. So for example, if this charge was already moving, you kind of gave it a push towards the right, what would happen? Its potential energy would increase, but kinetic energy would decrease. It would slow down because it feels this repulsive force that's being acted. And again, the same analysis would hold here if all these charges were negative. If the source was negative and the test was negative, then we still have the opposite charges interacting. So we're kind of, we're starting here with our understanding of electric force and then making conclusions about how potential energy must be defined here. Okay, so, but what we like to do with potential energy is we like to think about how it changes as a function of distance. What is the distance here? It's the separation between the two charges involved. So here is a plot of potential energy as a function of r, which is that separation, for two like charges. Here's two positive charges. So let's try to understand or make sure that this plot is consistent with what we've been talking about. So first of all, this equation here, going back to 7A days, is how we mathematically describe that connection between potential energy and force. So far we've just talked about in the previous slide how potential energy or force points in the direction of decreasing potential energy. So that's where the minus sign comes in. So here we know that the force, because we're talking about two like charges, must be in the direction of increasing r, which means that the force is repulsive. It wants to separate the two charges. So this is the slope of the potential energy graph. The slope here we see is negative, but then this negative sign makes the force point in the plus r direction. So that's consistent, the fact that the slope is negative. But there's one more aspect, is the magnitude of the force. How do we know the magnitude? Well, that's related to the magnitude of the slope. So we see that for large R, this graph is less steep, and for small r, it's more steep. So what does that tell us? It tells us that the force is stronger at small separations. So that's exactly what we've kind of observed with our experiments, is that when the two charged objects are close together, the force is stronger. The farther apart they get, the force becomes weaker. And it turns out that the exact relationship between this potential energy and the two charges involved is this. It goes as 1 over r. And then having this potential energy expression, eventually we can solve for the actual force. So K here is a Coulomb's constant, and you'll explore this more in DL. Q1 and Q2 are the two charges involved. So to have a potential energy, you must have a force, and to have a force, you must have an interaction between two objects, where these two objects are these two charges. So the stronger the charges are, charge has units of Coulomb, the stronger they are, the bigger will be the potential energy. But then the farther apart they are, the smaller will be the potential energy. So there are two effects here. And the plot, again, we see here is for two like charges. So if Q1 and Q2 are both positive, or Q2 and Q1 and Q2 are both negative, you still get the same overall sign. Now, if you had opposite charges, and I want you to think about how would that change this plot. So if one of these had a negative sign, then there would be an overall negative sign in the front. So think about what it should do with this plot. What then this plot, the way it would have to look like, it would have to be getting smaller or bigger and bigger for increasing R, which tells us that the force points in the direction of decreasing R, because that describes an attractive force. So think about how that potential energy plot should change for when the force is attractive. All right. So now we're going to do something a little bit abstract or a little bit different, but it will sort of all come together once we introduce electric forces, and specifically electric fields. So what we're going to define is what is known as the electric potential, also known as voltage. And voltage is something that's familiar back from circuit days, and I'll make that connection shortly. So how are we going to define this? Well, so the potential energy is something that's experienced between two charges. But now let's kind of separate the role of these two charges. We will say that there's one charge Q2, and that's going to be what we call our test charge. And then there's going to be a charge Q1. So we're just kind of taking this equation and splitting into these parts. And what we're gonna define this to be as the voltage which is generated by charge Q1. So in other words, there is the source charge Q1, which generates an electric potential or voltage. These are just two different ways of calling the exact same thing. We will typically probably refer to it as voltage because the word electric potential is very similar to electric potential energy, although the two things are, as you will kind of work with them more and more, are very different. So basically what we're going to say is that imagine there's just one charge out there in space, and that one charge can't do anything. It can't exert a force. It can't interact with anything unless there's another charge present. So it by itself doesn't do anything, but we can kind of theoretically say, well, it generates this voltage everywhere in space. And then if we bring now, and that's how we define that voltage. Now let's bring a test charge Q2 in that space where that voltage field, and we'll define the word field shortly, exists, so that test charge Q2 experiences a change in potential energy, this delta P, as it moves through this voltage. So you can imagine there's some charge Q1, there's a voltage defined everywhere in space. Imagine now putting this charge Q2 in that space and moving it around. As it moves around, it's going to experience a change in potential energy. Q2, which is that charge here, due to a change in voltage as this charge moves. So remember, when we talk about potential energy, we mostly care about how that potential energy changes as your object moves around. All right, let's now kind of connect those abstract ideas to what's a little bit more familiar to us in the context of voltage, and that's a circuit. So remember, this is kind of your standard, very basic circuit diagram. We have a battery, which has a positive and a negative side, and then we have a resistor. As current moves through this resistor, what we have learned in 7b is that there's a drop in voltage. So we can think about the battery as sort of is like our source, which generates this voltage. So it's always going to be true that the voltage drops if we go in the direction from the positive to the negative side. But what we think about is, well, what is changing its potential energy? What's changing its potential energy are the test charges that move through this voltage. So what are test charges? Well, there's either current, which is kind of the wrong thing, but that's how we define it as if it's positive charge moving. In reality, it's electrons or negative charge moving, but because we mostly talk about current when we talk about circuits, let's think about current first. So current is positive charge, so there's your positive test charge. As it moves clockwise here, it's going to experience a drop. There's a negative change in voltage. So there's the absolute value, but just to show that the voltage drops. So if we now multiply positive Q times a negative delta V, we see that the change in potential energy is negative. So this charge has a decrease in potential energy as it moves through the circuit. Now, if we're thinking about positive charge, oh wait, oops. Okay, so I'll fix this, but this should say negative charge. I must have just copied this over and forgot to change it. So electrons, negative charge, which way they're gonna move? They're gonna move away from the negative side of the battery towards the positive side of the battery. Now remember, voltage is something that's a source, so that's gonna always still decrease in that direction. So as this charge moves counterclockwise, because we're going from this point to that point, that defines an increase in voltage. So there's a plus sign, but it's a negative charge, so the Q is negative. So again, the potential energy drops. So you see, regardless of whether we're thinking about charge, positive charge, or current moving this way, or electrons moving the opposite way, there's a drop in potential energy. And that's what is physically relevant, because what happens is that as this electric potential energy drops, some other energy increases, like thermal energy, let's say, which, so this electric potential energy, in a sense, is being converted to, let's say, thermal energy. If we're talking about a light bulb, the filament of the light bulb warms up and then it radiates light. So this is how our circuit lights up a light bulb, for example. So just kind of connecting this idea of voltage to the circuit. So another thing that's going to be important for us to define is this idea of fields, because what I just talked about when we described voltage is that we have some source charge which is sitting there, and it's generating this voltage everywhere in space. So basically we're defining a quantity which has a value everywhere in space. And that's basically what a field is. And what we will learn shortly is that fields can be both scalars, so just numbers, or they can be vectors. So voltage is a number, so that's a scalar field. But we will see next week when we talk about forces, or specifically electric fields, those are going to be vectors. So just from your kind of everyday experience or knowledge, an example of a scalar field would be a temperature map. So you know, when you watch the weather forecast, you look at a map of the United States and you see, you know, what the temperature is everywhere in space. Of course, when you actually represent this, you would only put a couple of numbers there just to represent that temperature field. But in reality, this is continuous. Every point in space has a value of temperature. So it's not that, you know, only over here there's a temperature and over here, they're everywhere. But to make a simpler representation, of course, we just choose a couple of numbers where there's a significant change. So because temperature, again, is a scalar, it's just a number. This is an example of a scalar field. But you can also have a vector field. So wind, a wind velocity is a vector. So a wind has a direction. And it also has a magnitude. So here all the arrows have the same length. So this particular example of a vector field does not really incorporate the magnitude aspect of it. But normally you would have something, again, that shows you the direction, but then there's also a magnitude, a value, you know, how strong is the wind associated with each point. So vector fields is something we'll discuss next week. So this is why it was kind of easier to start talking about voltages and potential energies first, because they're scalars, but then next week when we make the connection to forces, we'll have to discuss vectors again. All right. Now, how do we, so, you know, with temperature and wind, we just see like an example of how we would represent it. We have a map, we put a bunch of temperatures where there's significant difference. Same here with velocities. But what about voltages? What's a good way to represent your voltage, which is our scalar field? Do we just put a bunch of random numbers in space, or is there kind of a nicer way to represent it? So the way we represent it is using what is known as equipotential lines. So we draw lines where this potential or the voltage is constant, where it's not changing. So this is very similar to a topological map that you've probably seen before. So what this topological map tells us is the topology of a given area in space. In other words, how the slope changes. So one thing, so these lines here, so if you look at a particular line, they represent a region of constant height. So constant, you know, elevation. So this is like, you know, a valley, you're just walking in a straight line. So that's where all these individual lines, so you can kind of follow where your elevation is not changing. Another thing that you notice about this topological map is that, like, right here, the lines are much denser than right here. So what does that mean? Well, we kind of know from, if you've ever looked at these maps, that this means that the slope is very steep. So there's, you know, probably you're getting close to a peak of a mountain where there's the change is very rapid, the change in the slope. Where here, it's probably a valley, so the change is not as rapid. So why does it happen that way? Because the distance between any two neighboring lines represents the same change in height. So here you have to walk much longer to get to that same change in height compared to here. So because here you walk for a very short time to get that same increment in elevation, this area is much steeper. So these same ideas will translate to our equipotential lines when we talk about voltage. So let's go back to this plot where we represented voltage as a function of separation, and we saw that it follows this inverse relationship. It follows inversely as 1 over r. And think about and this is for point charge. Remember, just when you had one charge sitting there in space, that one charge generates this voltage around. So the farther you go, the smaller that voltage will be. So let's see how we would draw these equipotential lines. So we know that, for a given distance away from that charge, there is a specific voltage. So for drawing a two-dimensional equipotential surface, what we would have is we would have like the center representing the charge and circles with the same radii representing the equipotential lines. You'll see that shortly. But what else do we need to be careful about? We need to be careful about how this voltage changes with distance. So what we want to keep constant is that any two neighboring equipotential lines have the same change in voltage. The same way for a topological map, any two neighboring lines had the same change in elevation. So when r is small, to go, let's say, from 2 tick mark increment here, we have a very small change in r, right? So that means it's sort of, you don't have to walk far to have that voltage change. Kind of like when a mountain is very steep, you don't have to walk really far. That distance is not really far when the elevation change is very rapid. Now, for larger r's, because this goes as 1 over r, we see that 2 tick marks here represent, so the 2 green dashed lines here represents a much larger r. So that what that tells us is that as we go away from that charge, for that same voltage difference, the difference in r has to be bigger. So how do we represent this? And we represent it exactly with these concentric circles. So what these lines represent is your equipotential. Remember, potential is the same. It depends on the distance from the charge. So here we have our source, which is our positive charge, which is a positive charge here. So any distance, that's the same, so the radius of the circle represents some distance r, and that's where the potential will be the same. Now, how is the idea that the potential changes much more rapidly with small r is represented here by the density of these circles? We see that when we're close to the charge, these two circles, to have a change, let's say in 1 volt, this delta r is very small. Kind of like if we go back here, delta r is very small to have that same change in voltage when the r is small. R is small when we're close to the charge. As we get farther away from the charge, to have that same change in voltage, that represents a much bigger change in r. So you could see that these circles get farther and farther apart as we go away from the charge. Now let's look a little bit more at these numbers. So the way that this is labeled, again, it's arbitrary, but what this tells us is that, so I just chose some numbers, but we want to make sure it's consistent with this equation. So what this tells us is that when r gets very large, v will go to 0. So that's why we start when r is small, v is large. So we start with large values of v, and then they decrease as you go away from the charge, but they're always positive because our test charge q is positive. And then here it also kind of is going to tell us about force indirectly, and we'll make again this connection a little bit more next week, but we see that here it's representing where it's less steep, because for the same change in delta P, we have a much bigger change in delta R. So it's going to be less steep, except this is potential energy. So, you know, we have to have another charge. We'll get to that shortly. But smaller slope or less density in equipotential lines will make that connection to the fact that the force is weaker as well. So we'll see, again, we'll talk more about it next week, but as this density of equipotential lines decreases, so does the force. All right, and I'll just end, as I promised, it's going to be a short lecture. So I'll just end here with you kind of thinking about what happens when we introduce a test charge. So remember, all these equipotential lines tell you here is that we have one charge and it generates this voltage everywhere in space. So now what happens when we bring another charge, we call this a test charge, in these equipotential lines, but be careful, these are not the same as in the previous slide. Look at these numbers, now we have negative numbers here and they're getting less and less negative. So what this question is asking, given this negative charge that we put in these equipotential lines, what is the direction in which it feels a force? So these arrows show the possible directions of the force, or one of the options is that there's no force, doesn't feel a force, the force is zero. So let's think about this and let's discuss the answer. So there are several ways of thinking about this. So first, let's actually, as you saw here in the previous slide, I didn't tell you which charge, what type of charge, positive or negative, is generating these equipotential lines. In fact, once you draw equipotential lines, there's no reason to define what the source is. You don't almost care about what the source is because the equipotential lines already encode that information indirectly. So looking back at this, what we see is that if Q was negative and R is small, that's when the voltage is most negative. And then as R is getting bigger, it's getting less and less negative until it gets to zero. So for positive charge, it was most positive going to zero. Here it's most negative going to zero. So the voltage is decreasing away from this negative charge. So what basically this tells us, because we see it starting from -4 going to -3, -2, -1, that this must be a negative test or source point charge. So now the direct connection we know between force and voltage is this equation, which connects the change in potential energy to the change in voltage, where this Q represents our test charge. So we know that if we look at this negative charge, this is going to be a negative sign here. Now the voltage, so if we want to find the force, we want to figure out which way is the potential energy decreasing, because remember, force always points in the direction of decreasing potential energy. So this is negative because our test is negative. So we want to see where's delta V positive. And how does delta V increase when we go away from the charge? Because it's getting less and less negative, so it's increasing away from the charge. So if we look at this charge over here, we see that the voltage is increasing to the left. So that means the potential energy is decreasing to the left, so that must be the direction of the force. So we actually didn't even need to figure out that that's a negative charge. All we could have started with is the fact that the voltage is again increasing to the left because Q is negative, potential energy is decreasing. Now, since we did actually figure out that the charge is negative, we could just use this idea that opposite charges repel. So because they repel, this negative charge wants to go away from this negative charge. So again, the force is going to be in the direction away from that negative charge. Another kind of subtle thing, and I'll discuss it a little bit more next week, is the fact that forces always have to point perpendicular to these equipotential lines. So you can't have any component of the force which is along the equipotential lines. And basically the idea behind that is that force equals to the rate of change of potential energy. So if there's a component of the force, remember force is a vector, which is along the equipotential line, that's when there's no force, because equipotential means potential energy is not changing. It's the voltage is staying the same, so it's a potential energy. So that kind of tells us that the force always has to point perpendicular to equipotential lines. All right, so I'll be done for today. Again, just so you kind of get introduced to this slowly, and there will be more next week. Thank you for